So, next we discuss Helmholtz free energy. Helmholtz free energy is a concept in thermodynamics where the work of a closed system with constant temperature and volume is measured using thermodynamic potential. The Helmholtz free energy can be defined as U minus Ts. The change in Helmholtz free energy, we write delta U is delta A is delta U minus T delta S. Again, this is at constant temperature, at constant T. Okay. Actually, this from this expression we get delta A is delta U minus T delta S minus S delta T. So, if temperature is constant, so at constant temperature we write delta T is 0, delta T is 0. Okay, so we get delta A equals to delta U minus T delta S. That is why it is written. Next we discuss some problems. First problem is the oxidation of iron occurs like this: 4 Fe plus 3 O2 gives 2 Fe2O3. The enthalpy of formation of Fe2O3 is minus 824.2 kilojoule per mole, and the entropy change for the reaction is minus 549 joule per Kelvin per mole at 298 K. In spite of negative entropy change of this reaction, why the reaction spontaneous at 298 K. So, to check the spontaneity of a reaction, so we know delta G as at constant temperature pressure has to be lower less than 0. So, we know delta H minus delta T delta S, delta G is delta H minus T delta S. So, we can write now delta H minus T delta S. Overall this thing has to be less than 0 for spontaneous process. So, delta H has to be lower than T delta S, right, for spontaneous process. Now, what is the value of delta H? So, here delta H is minus 824.2 kilojoule per mole, and then if we convert it into joule, so we get minus 824.2 times 10 to the 3 joule per mole, and delta S is minus 49 joule per Kelvin. So, T delta S is minus 49, here T is 298 K. So, T delta S is minus 549 times 298, this is in joule unit. Okay, so, if we multiply this, okay, so we get, so if we see now, if we see this, we see that, okay, so this is the value of this one, T delta is lower than this one. Okay, so we see that delta H is lower than T delta S. So here you see that T delta S, you have the negative sign also. Okay, so this means this is this T delta S value is greater than delta H. Okay, so that's why the process is spontaneous. Now, next problem is predict whether it is possible or not to reduce magnesium oxide using carbon at 298 K according to the reaction MgO plus C gives Mg plus CO. Delta H or this reaction delta H naught is given minus 491.18 kilojoule per mole, and delta S naught reaction is also given 197.67 times 10 to the minus 3 kilojoule per Kelvin per mole. If not, at what temperature does the reaction become spontaneous? So, we write, so delta G, we know that delta G not reaction is delta H minus T delta R S naught. Okay. So, the value of this one is minus not minus 491.18 kilojoule. If we convert into joule, we get 10 to the 3 minus, okay, we can write in kilojoule also because everything is given in kilojoule unit. So, we can write kilojoule also, this is in kilojoule unit. And then next is T is given, okay, so T is 298 in kilojoule. T in kilojoule is 298 times delta S is 197.67 times 10 to the minus 3, and the value is kilojoule per mole. So, if we calculate this one, you get we get 432.29 kilojoule mole inverse. So, we see that delta G naught is positive here. So, since delta G naught is positive, so it is non-spontaneous. The reaction will be non-spontaneous. So, what we need to do? So, here delta H is positive, you see, and delta S is also positive, but T delta S has to, there is a negative sign there in front of T delta S here. So, this T delta S has to, the value of T delta S has to overcome the value of delta H naught, then only the reaction will be a spontaneous one. Okay. So, in order to reaction become spontaneous, delta H has to be lower than T delta S, right. So, T has to be greater than delta H by delta S, right. So, the temperature, minimum temperature required is the temperature above which the reaction will become spontaneous is 491 delta H, right. So, 491.18 by 197.67 times 10 to the minus 3, this Kelvin. So, if we calculate this one, we get 2493 Kelvin, 0.4 Kelvin. So, the temperature has to be more than 24, the temperature has to be more than 2493.4 Kelvin, has to be more than 2493.4 Kelvin. For the melting of ice at 25 degrees Celsius, the enthalpy of fusion is 6.97 kilojoule per mole and the entropy of fusion is 25 joule per Kelvin per mole. Calculate the free energy change and predict whether the melting of ice is spontaneous at this temperature. Okay. So, delta G is your delta H minus delta S. So, what is the value of delta H here? So, delta H is enthalpy of fusion, so heat is giving solid to liquid, so it is positive. So plus 6.97 times 10 to the 3 joule in joule unit minus T is 298 K, temperature is 298 K, and then delta S is 25.5. Okay, so if you calculate this one, you get roughly minus 0.5, approximately 0.5 kilojoule mole inverse. So since delta G is negative, the melting of ice at 25 degrees Celsius is spontaneous. Next problem is, for the reaction A plus B gives C plus D plus Q is found to have positive entropy change. The reaction will be possible at high temperature, possible only at low temperature, not possible at any temperature, or possible at any temperature. It is possible at any temperature because a reaction with positive entropy change increases disorderness, right, and releases heat. So it happens spontaneously at any temperature. The next problem is, a Carnot heat engine works between 300 Kelvin and 600 Kelvin. It consumes 100 joules in each cycle. What is the heat rejected in each cycle and what is the work done? So we know that Carnot engine, okay, so it involves with 4 steps, right. So here T1 is given, T1 is 300, works between 300 Kelvin and 600 Kelvin. If we say the hot engine T1 is 600 reservoir, okay, and T2 is 300 Kelvin, okay, and Q is 100 joules. Okay, so efficiency eta is 1 minus T2 by T1. So you get 1 minus 300 by 600. So you get 50%. The work done is related to eta is W by Q1. So you get W is eta times Q1. So you get, what is the value of eta? Eta is 0.5, and what is 0.5 we can write here, 0.5, and what is the value of Q1? Q was is 100, right. Okay, so we get 50 joules. Let the heat rejected be Q2. So Q2 is 100J minus 50J, so it gives you 150J, right. Because for other two steps, these are for isothermal steps. For other two steps, the processes are adiabatic, so Q is 0 there. Okay, so problem number 6, it says a Carnot engine operating between two reservoirs has efficiency of 1/3. When the temperature of cold reservoir is raised by x, its efficiency decreases to 1/6. The value of x if the temperature of hot reservoir is 99 degrees Celsius will be. So, temperature T1 is given. So, T1 is 273 plus 99, so gives you 372 K. So, eta is 1 minus T2 by T1, and efficiency is given, right. So, you get 1/3. So, you get 1/3 is 1 minus, okay, so T2 we need to calculate, and T1 is 372. So, we get T2 is 1 minus 1/3 times 372. Okay. So, we get 2 times 372 by 3. So, we get 124. So, 248 K. Now, when eta is 1/6, so we write 1/6 is 1 minus T2 by T1. So, it gives you T2 by T1 is 1 minus 1/6. So, it gives you T2 is 5/6 times 372. So, 62. So, we get 310 K. So, change in temperature of cold reservoir is 310 minus 248 K, so 62 K. Next problem is a Carnot engine with efficiency 50% take heat from a source at 600 Kelvin. In order to increase the efficiency to 70%, keeping the temperature of the sink in, calculate the new temperature of the source. Okay. So, eta is 50%, right. So, 1/2. So, efficiency 50%. So, we get 1/2. Okay. So, 1/2 is 1 minus T2 by 600. So, the value of T2 we get is 1/2 times 600. So, gives you 300 K. Now, when efficiency is 70%, when eta is 70%, means 7/10. So, we get T2 we know T2 is 300 K. So, 7/10 is 1 minus 300 by T1. This T1 is the new temperature of the source, right. This is the new temperature of the source. Okay. So, we get 300 by T1 is 1 minus 7/10, so we get 3/10. So, T1 we get 300 times 10 by 3, so we get 1000 K. So, this is the new temperature of the source. Next problem says, under what condition will a reaction be spontaneous if both delta H and delta S are positive and both delta H and delta S are negative. Okay. So, we already discussed briefly for different cases. So, we know delta G is delta H minus T delta S, right. So, we can have three cases rather. Case 1, when delta H is negative and delta S is positive. So, this is in this case delta G is less than 0 always, and the process is spontaneous. But case 2 is when delta H is positive and delta S is also positive. So, in this case, in order to have delta G less than 0, so delta H has to be lower than T delta S. Okay, so see in front of T delta S there is a negative sign. So, if delta H is less than T delta S and both delta H and delta S positive, so this whole quantity is positive, we have the minus sign here, so whole quantity will be negative. So, if delta H is less than T delta S, then only the reaction will be spontaneous. So, this is the answer of problem number 1. Next case is your case 3, when delta H is negative and delta S is also negative, right. So, delta S is negative means minus T delta S is positive, right. So, in order to have the process spontaneous, delta H value has to be greater than T delta S, then only we get delta G negative. So, only this case delta G is negative. Problem number 9 says, for a sample of a perfect gas when its pressure is changed isothermally from P1 to Pi to Pf, the entropy change is given by. So, for isothermal process we know, for isothermal process delta S is minus Nr. For an isothermal process this will be plus Nr ln V final by V initial. Okay. So, for isothermal process, so when isothermal process means T is constant, when T and N constant, so P is proportional to 1 by V, or we can write P I is 1 by V is proportional to 1 by Vi and Pf is proportional to 1 by Vf. So, this expression becomes delta S is Nr ln Pi by Pf. So, if that is the case, so B is the correct answer. So, B is the correct answer or correct option. Now, problem number 10 says the entropy change involved in the isothermal reversible expansion of 2 moles of an ideal gas from volume 10 decimeter cube to a volume of 100 decimeter cube at 27 degrees Celsius is. So, for isothermal process for an ideal gas and isothermal process, change in entropy delta S is nR ln V2 by V1. Now, here N is number of moles of gas and equals to 2, and V2 is the final volume, is 100 decimeter cube, means 100 liter, and V1 is initial volume, is 10 decimeter cube, is 10 liter. So, delta S is 2 times value of R is 8.314 and ln 100 by 10. So, we get 16.628 ln 10 in joule per Kelvin. So, this is the value of delta S. So, if you calculate this one, you get basically delta S is 38.3 joule per Kelvin. So, problem number 11, it says a typical resisting person heats the surroundings at a rate of 100 watt, where 1 watt is 1 joule per second. Estimate the entropy the person generates in surroundings in the course of a day at 300 Kelvin temperature. So, what is the Q reversible for surroundings? So, it heats the surroundings, means surroundings is gaining heat, so it is positive quantity. So, Q surroundings, right, is per second it is generating 100 joule per second, okay. And then if we can multiply with 60, means per minute, 60 per second per hour, and then 24 hour, because one day is like this, okay. So, this is Q surroundings, and if the process is reversible one, you can write Q reversible, okay. So, delta S surroundings is Q surroundings reversible process by T. So, 100 times 60 times 60 times 24, and temperature is 300, this is joule per Kelvin. So, if we calculate this one, we get 28.8 kilojoule per Kelvin. Problem number 12 says a reversible engine converts 1/6 of heat inputs into work. If the temperature of the sink is reduced by 62 degree, its efficiency is doubled. Find the temperature of the source and sink. So, the efficiency of heat engine we know the efficiency of the heat engine is eta is 1 minus T2 by T1, right. So, 1/6, it is efficiency is 1/6 1 minus T2 by T1. So, you get T2 by T1 is 1 minus 1 by 6, so we get 5 by 6. Suppose this is equation 1. Now, if eta prime is the efficiency of the engine, when the temperature of the sink is reduced by 62 degrees Celsius, we can write eta prime is 2 times 1 by 6 So, we get 1 minus T2 minus 62 by T1. So, we get T2 minus 62 by T1 is 1 minus 1 by 3. So, we get 2 by 3. This is equation 2. Okay. So, if we divide equation 2 by equation 1, so dividing equation 2 by equation 1, so if we divide it, so T1 gets cancelled. So, we get T2 minus 62 by T2 is 2 by 3 times 6 by 5. Okay. So, we get 4 by 5. Okay. So, if we solve this one, we get T2 is 310 Kelvin. Okay.